So, our new chapter, chapter 15. So, chapter 15, if you look at the title, it says it's the study of conjugated systems, orbital symmetry, and ultraviolet spectroscopy. So, we're going to be getting to another instrument. So, when I've reviewed this chapter, I've broken it down into like 4 different parts. So, I have part 1, we're going to study conjugated systems. And then what I'm going to prove to you is conjugated systems are more stable than we would predict. So when I say conjugated, what does that mean to you? It should mean something. What does that word conjugated mean to you? Yeah, so benzene is one. So, and then I heard some of you say alternating double bond. I think I heard, or maybe it was my imagination, alternating double bond. So those are conjugated systems. Whenever I have alternating double bonds. So chapter 15, more of the focus of chapter 15 is on aliphatic conjugated systems. I can't talk and plug in at the same time. There we go. Okay, aliphatic. So what does that word mean to you if I'm talking about aliphatic conjugated systems? Yeah, straight chains. 16 aromatic conjugated systems. And so then what does that mean to you? No, exactly. Yeah, so like our benzene ring. And so then chapter 15 and 16 are very related to one another. Aliphatic conjugation and aromatic conjugation. So our focus is first on aliphatic. So the next thing I want to talk about, which is, I say here, we're conjugated. Okay, so we've reviewed that word, what conjugated means. So next thing, I say that we're going to study p orbital overlap. So what is the shape of a p orbital again? Yeah, so I have that bilobe shape. So I'm going to go ahead and draw one p orbital like this. Okay, if we're going to be talking about p orbital overlap, it means I need to draw a second p orbital. What do p orbital overlaps look like? Are they linear or are they parallel? So do they overlap like this way? Do they overlap this way? Which way is it? So parallel. So it's always parallel overlap. And so I would need to draw that second p orbital underneath like this. So on paper, can I draw out linear overlap? Well, sure, I can draw it out, but such an overlap does not exist. All of our overlap is parallel overlap. So we're going to look at drawing the overlap of orbitals. Elliot? No, so sigma bonds, the only sigma bonds that we know of are like sp3, sp2, sp. There are no such thing as a p to p sigma bond. It doesn't exist. Oh. But you are right, the linear overlap is how I would draw a p overlapping with p sigma bond, but such a thing does not exist. There has never been any evidence of it. The only evidence we have is pi bond with parallel overlap. And so that is the only kind of orbital overlap that we draw. Okay, let's talk about part 2. We're going to then go into a unique chemical reaction, and we're going to get to this today. It'll be very quick. And then I have a 2-page take-home worksheet that's a warm-up for Wednesday. So we're going to be introducing the one unique chemical reaction of the conjugated alkenes. So then part 3, we're going to talk about UV light, so spectroscopy and conjugation. And then the last 4, we're going to do just a little bit of review of SN1, SN2, and free radical chemistry of alkenes, because it's never too early to start studying for the final exam. So that's going to be the 4th thing that we do. So I want to start into the part 1. I have a place that we'll take a break. And then we'll come back and finish with the part 1 material, and then I'll introduce part 2 material, so our interesting chemical reaction. Okay, so getting into part 1, analysis of a conjugated diene structure. So we're going to begin our analysis of conjugated dienes by thinking about the simplest diene, which is 1,3-butadiene. So my 4-carbon diene. The most stable conformer of the 1,4-butadiene, or sorry, 1,3-butadiene is the one that I have drawn up here, S-trans. So let's talk a little bit about this naming system. So S stands for single bond. I have a single bond in the middle of two double bonds. The two double bonds are in trans orientation because one is below the plane of the single bond, the other is above the plane of the single bond. Let me come in with my highlighter. So here would be the plane of the single bond. And you can see like one is above, one is below, or you can talk about it as one's to the left and one's to the right, but that's my plane of the double bond. So what does the s-cis look like? And then Elliot, I'll get to your question. So s-cis. So s-cis, what does it look like? So it means I have a single bond, and then those two double bonds, how are they both arranged? Since I used the word cis. Same side. So I would have a double bond over here, and then I would have the double bond over here. And then, of course, it also has all of the hydrogen atoms. I have an H, and then I have an H, and I have two hydrogens here, and then I have two hydrogens here. And so this would be s-cis. Okay, so we can freely rotate between these two at room temperature. Cold, the lowest in energy, which do you think? The trans or the cis is lowest in energy? Trans, big groups far apart, trans is lowest in energy. But at room temperature can both go through both conformers. Okay, some unique things. So, with this 1,3-butadiene, carbon 1 to 2, so I'll label over here, carbon 1 to 2 has the normal length for a double bond. Carbon 2 to 3, shorter than the typical length of a single bond. And then 3 to 4, typical length of a double bond. So one thing that's very odd about butadienes, this single bond in the middle is shorter than we would expect. There's another thing that's also very unique about 1,3-butadiene, which is I would look at it and go, oh, wow, I have two double bonds. So if we think back to our alkene chemistry, so I have a double bond, and then we even did this like in lab. We did the bromine decolorizing test. And we talked about how I would have the pi bond attack of the bromine, I would break that at a bond to the bromine, and then what happens to the purple color when we have an alkene present? That goes away because we easily react. Well, here I have two double bonds. So what might you think about the reactivity? What might you think? Yeah, it seems like it'd be very reactive, but guess what? It's less reactive than a normal alkene. It's also very curious and unique. So there are two unique things about conjugated systems. The first being that the bonds are not the length we would typically predict, and the reactivity is also not the level of reactivity we would typically predict. So some single bond lengths are shorter, and overall, these conjugated alkenes are less reactive than the typical alkene. Okay, Elliot, your question, or did I already get to it? Okay. Okay, everybody good? They tell you these two fundamental facts that are curious about the butadiene. So we're going to get to answering the question, why? Why does this happen? Yes.
And it's not just with butadiene.
It's
right?
any conjugated. Any conjugated has single shorter we predict and reactivity lower than we would predict. What I first want to show you is kind of the proof regarding reactivity. So let's start with the normal alkene studies. So when we study alkenes and the heat of hydrogenation, this would be the heat that's released when we add hydrogens. So I have the data here for 1 pentene. So I have a double bond at the end of a structure, and it releases 30 kilocalories of energy. If a double bond is in the middle of the structure, it releases 27.4 kilocalories of energy. So what if I have a structure with one bond at the end, one double bond in the middle? What would I predict for its energy? So it'd be, again, doing 27.4, which is 57.4, right? And so then if I go to some other representative examples, oh look, here I have this diene system. So I have a double bond at the end, a double bond at the middle, and look at how much energy is exactly released. 57.4, exactly what we would predict. And look at this other isolated diene. I have two ends, so that's like a 30 plus 30, and look at how much energy I exactly get, 60. But what happens if the end double bond and the middle double bond are conjugated? Does it fit the amount of energy I would usually predict? It doesn't. I release less energy. So what that means is my predicted energy is, I have my energy diagram, my predicted energy is this. That would be my prediction, but what is my experimental data? I release less energy, which means the starting material is lower in energy. I go over an energy barrier and end up at that product. So that's my experimental data. And so what this means is that our dienes, our conjugated dienes, are more stable than we would usually. And this is the study that proves. Okay, so then this is the fact. And then that still leads us to wanting to know, the big question is, why? Why are these more stable than we would predict? And in order to understand stability, and so then this will be like our cliffhanger for after the break, in order to understand stability, so kind of if we have stable molecules with short bonds, it means we have very strong bonds. And so in order to evaluate the strength of a bond, we have to evaluate the orbitals forming those bonds. And so when we come back, we're going to do drawings of orbitals. We're going to be doing lots of drawings of orbitals over the next couple of days. And so we're going to start with drawing the energy diagram for ethylene, so a 2-carbon system. And then we're going to draw for our 4-carbon system to better understand it. Okay, so we'll come back at a quarter after, and we'll start with drawing energy diagrams of molecular orbitals from carbon. Okay, let's go ahead and start with learning about how we evaluate the bonding patterns of conjugated systems. So we're going to start with ethylene. So ethylene is just very simply, I have C double bond C, and we are just evaluating the pi bonding system. So here's how the process works. We're evaluating the pi bonds within a structure. So first we begin with how many p orbitals are within this molecule. So I know I have a p orbital at this carbon and I have a p orbital at this carbon. So how many p orbitals do I have? I have 2. So I have 2 p atomic orbitals. What that does mean is for my energy drawing, I need to create a drawing with 2 pi molecular orbitals. So here's how that works. My energy drawings, I'm going to go here, and I have a certain amount of energy in the system. I have a p orbital and a p orbital for the 2 carbons, because I'm evaluating C double bond C. So what is the lowest energy kind of overlap they can form? Constructive orbital overlap or destructive orbital overlap? And everyone screams, runs out of the room because you thought we were done with this at chapter 2. So what kind of orbital overlap is lowest in energy? Constructive. How do I draw constructive orbital overlap? So keep in mind, each lobe has a phase. So I'm going to put this, my top lobes, I am arbitrarily choosing my top lobe is going to be a positive phase, and my bottom lobe is of negative phase. And remember, this is mathematical phases of a wave. So wherever I put a plus, what should that make us think of in terms of wave mass? Okay. So if I have a wave, waves go up and down. So a plus would mean up, and so then I think of it as a crack. And so then if I go down, it is a trough. So this is all math, wave math. So a plus is a crest of a wave, and then a trough is the negative phase of a wave. And so I draw the phases. So in this second carbon, how do I need to write the phases so as to represent constructive orbital overlap? I need to put a plus on the top, a minus at the bottom. There is another way that visually orbital overlaps are done. And so that would mean wherever we have a plus phase, it gets filled in. And whenever there's a minus phase, it's left empty. So this also represents a constructive orbital overlap. So either two pluses overlapping or two colored lobes overlapping. Okay, so I have two p atomic orbitals. There are two ways that I can arrange their overlap. So I've just arranged all constructive orbital overlap. What is the second way we can arrange the orbital overlap? All destructive. Okay, so then that is going to be a higher energy orbital overlap. So at a higher energy, I need to draw my two p orbitals. I always arbitrarily choose to make the top lobe of my first one be plus. And then I usually don't draw in the minus into the other orbital, it just gets tedious. So then I know to represent destructive orbital overlap, what sign do I need to put at the top lobe of the second carbon? Yep, a minus. And for destructive orbital overlap, what forms in between the two of them? A node. And they always get drawn into an energy diagram, usually with a series of dots. Okay, so for a two-carbon system, drawing the molecular orbital energy diagram is easy. I have two p orbitals. They can be arranged in two different energy levels. So this would be the drawing. I want to add in some other labels. So the lowest energy molecular orbital is always labeled as pi1. So then this next one, what should it be labeled as? Any guesses? Pi2. Okay. So I have an even number of molecular orbitals. What we know from studies is that right in the middle, we often draw an energy line. Right in the middle, that is the energy of what would be a free radical unbonded p orbital. So all of the orbitals below are more stable than a free radical. And then all those above are less stable than a free radical. Okay, and so then that's kind of an orientation for our energy diagram. What we also do with our energy diagrams is we like to figure out where are the electrons? How do the electrons fill in? So every carbon donates one electron. So how many total electrons do I have in the system? I have 2. So I have electron 1 goes in pi1. Where should electron 2 go? With all those rules, alpha, Pauli's, all of those principles, where does electron 2 go? Yeah, it goes into the same one. I always fill in the lowest energy orbitals before I put electrons into higher energy orbitals. So that means my second electron goes here. Okay, so pi1 has electrons within it. And so it is called a bonding molecular orbital. any orbital that has electrons in it is known as a bonding molecular orbital. And so any guesses as to like the name of orbitals that are without any electron density?
Non-bonding.
Instead of non-bonding, it is, I heard the word anti-bonding. So sometimes this energy line is called the bonding anti-bonding line. Anything below it is a bonding molecular orbital. Anything above it is an anti-bonding molecular orbital. Okay, pi2, now we've identified that pi2 is an anti-bonding orbital, so we add another label. We call it pi2 star and add an asterisk. So if I'm ever talking about like a pi2 star, now you know I'm talking about an anti-bonding orbital that at ground state has no electrons. Okay, so this is a pi energy diagram for ethylene with all of the details. 2 p orbitals arranged 2 different ways. I have a total of 2 electrons. They both fill into pi1. So pi1 is a bonding orbital. It is below the energy of a free radical p orbital. And then I have pi2 star, which is an anti-bonding orbital, and it is above higher in energy than what would be a free radical electron. But at ground state, my molecule behaves as if it pi1 is just totally defines how my molecule behaves. And I see in pi1 I have total constructive orbital overlap, which means that I definitely have a very strong double bond between these 2 carbons. Okay, so now let's compare and contrast. So now let's do 1,3-butadiene. So for me, new page. For you, maybe also new page. So for those of you who like to go through my PowerPoints, I walked through all my details right here that you can come back to. Okay, so now let's do this 4-carbon system. So I have C, double bond C, single bond C, double bond C. So pi bonds are formed by p orbital overlap. What I like to do for myself is I draw, okay, I have a p orbital there, those are overlapping to get that pi bond. I have a p orbital here, I have a p orbital here, those are overlapping to get the second pi bond. So now let's draw our energy diagrams. How many p orbitals in total do I have? So I have 4 p atomic orbitals. So in this energy diagram, how many pi molecular orbitals do I need to draw? Yeah, 4. So math is easy. There are 4 ways to combine these orbitals, 4 different ways to combine the p orbitals. So I know that I'm going to be drawing a pi1, so I'm just going to sketch it out. There's my 4 of pi1. What am I also going to be drawing? 2, 3, 4, a pi2. What do I also need to draw to fully understand this conjugated system? I need to draw a pi3. Oh yeah, and you're right. So then here's going to be that energy level of a free radical because I have an even number. So then what's going to be above that line? And Luke, what do I label this as again? I heard you murmur it. Yep. And then what else do I need to draw to be very complete in my drawings? Okay. So I have sketched my energy diagram. Now we need to fill in the details. What is the lowest energy way for us to do orbital overlap of all 4 of the p orbitals? They should all be what kind of orbital overlap? All constructive. And so since I like to use mathematical signs, and I always begin with my first with a plus on the top. Carbon 2 should be what on the top? Carbon 3A, carbon 4A. Okay, that's pi1, all constructive orbital overlap. Okay, what does pi2 look like? Well, So pi 1, all constructive orbital overlap. What would be like the next highest in energy? If I had 1 destructive orbital overlap, and what we know from studying the molecules is that when we move up in energy levels, we add 1 destructive orbital overlap in a symmetric position. So looking at pi 2, where am I going to have destructive orbital overlap between which 2 carbons? Yeah, between carbon 2 and carbon 3. So what I like to do is I like to draw in, I'm going to do destructive overlap and form a node right there in pi 2. So now to fill in the phases in the top, plus, and then plus, but I hit a node, an area of destructive orbital overlap. So then what sign needs to be on the other side? And then what needs to be in 4? Negative, right? Because between carbon 3 and carbon 4, I have constructive orbital overlap, which can mean negative overlapping with negative. Okay, so that's pi 2. So pi 3, what is pi 3 going to look like? How many destructive orbital overlap should there be within pi 3? 2. And there are places of symmetry. Where does it look like I could put 2 nodes in places of symmetry? Yeah, 1 to 2 and 3 to 4. So let's draw those in. So 1 to 2, 3 to 4. Right, and so I'm going to go plus, and then what needs to come next? And then what comes next? And then what comes next? Another plus. Okay, that's what pi 3 looks like. So pi 4, how many nodes are going to be within pi 4? How many areas will I have destructive orbital overlap? 3. And let's see, places of symmetry. Oh, it's going to be at each one. So 1, 2, 3. So what do these phases look like? Plus, then, there we go. So there's pi 4. So I'll highlight pi 1. The lowest energy molecular orbital is always all constructive orbital overlap. So the highest energy level is always all destructive orbital overlap. And then how many nodes do I increase going up per molecular orbital? 1. Yep. And so if I were to like randomly have you draw pi 10 of a huge conjugated system, how many nodes are you going to need to draw into pi 10? Yep, 9 nodes. Will I ever have you draw pi 10? Maybe not.
So,
but would you have to draw pi 1, pi 2, pi 3, pi 4, pi 5, pi 6, pi 7, pi 8, pi 9 in order to figure out what pi 10 looks like? So you know that I would have so many carbons going across, you would need to add 9 nodes, and so you could draw it without drawing all of the others, which decreases the tedium. Yep.
so is that pi 4?
Oh, that's exactly where we're going. So Isaac just asked the question, is pi 4 also pi star? Let's figure it out. So I have 4 carbons, so 4 p orbitals. How many electrons are in this system? The math is really easy. I had 4 p orbitals that join together to make 4 molecular orbitals. And how many total electrons will fill into this diagram? 4 electrons fill in. Okay, electron number 1 goes into pi 1. Where does electron number 2 go? Pi 1. Where does electron number 3 go? Where does electron number 4 go? Pi 2. And so actually to get to Isaac's question, pi 3 is actually what kind of orbital? Bonding or anti-bonding? Anti-bonding, so we should also write pi 3 star. Pi 3 is a star orbital, an anti-bonding orbital. And then what is pi 4? Yep, anti-bonding. Okay, how in the world does this help us understand why bonds are short and why things are stable? I'm sure you've wondered that. Or maybe I'm not even sure the point of doing this drawing, but let's go through and evaluate. So between carbon 1 and carbon 2, looking at all of the pictures of the bonding between carbon 1 and carbon 2, do I have a nice, strong pi bond? So carbon 1 to 2 in pi 1 shows us, yep, I have good constructive orbital overlap. What about pi 2 in carbon 1 to carbon 2? What does it show us? Nice, good constructive orbital overlap. I have a strong bond, pi bond between carbon 1 and 2. So let's move over. What's happening between carbon 2 and carbon 3? Initially, I drew it as a single bond. But let's look at what's happening here. What does pi 1 tell us about the nature of bonding between carbon 2 and carbon 3? Does it have some pi bond character? It does. Look, I have orbital overlap between carbon 2 and carbon 3. So that means I do have some pi bond character. But does pi 2 tell us? Do I have really strong pi bond character between 2 and 3? So it's not really strong, it's only kind of strong. Is there another word that we sometimes use for kind of? Yeah, intermediate, there's another word, it's with a P. Partial. We have partial double bond character between carbon 2 and carbon 3. How do we often draw partial double bond character? Like with little dots or with little dashes, so I'm going to add it. And guess what? When we go through and we measure the distance between carbon 2 and carbon 3, it is exactly in between the length of a single bond and a double bond. And so that length tells us we have partial double bond character. Okay, so then let's look at 3 to 4. So 3 to 4, what does our molecular orbital tell us? Strong bond. So now we have 3 options. Do I have a strong pi bond, a partial pi bond, or no pi bond between carbon 3 and carbon 4? Strong pi bond. Yep. So then I've just gone over why carbon 2 to carbon 3 has a shorter bond. So Alex, let me go one more thing and I'll get to your question. So why is this less reactive than we would expect? Now I see that I have pi bond character all the way across. What that means is the 4 electrons can circulate throughout this entire chain. So do I have 2 electrons that are localized only between carbon 1 and carbon 2, therefore making this very nucleophilic to do an attack? And the answer is no. My electrons are shared all the way across. I do not have 2 nucleophilic electrons localized at one place to do good chemistry. And so then that is why conjugated systems are less reactive than we would otherwise predict, because all the electrons are completely spread out. They're not localized in one area so as to do a nucleophilic attack. Okay, so Alex, your question?
I was going to ask you, partial pi bond is kind of like resonance?
Yes, and so then this is where our idea of resonance comes from. So yeah, we have that pi bond character. Those electrons resonate back and forth. So sure, at one instance of time, I might find the 2 electrons over here, but in that next instance of time, where can they resonate to? Maybe over here on the other side or more in the middle. Yeah, so that they resonate, they go back and forth all the time. And this is the concept of resonance. Yeah, because I have partial double bond character all the way throughout, and so those electrons can back and forth, and they're not localized to one different position. Okay, so your take-home project is going to be, you're going to draw for me larger systems. So we've practiced a 2-carbon system, a 4-carbon system, and then the worksheet I'm going to send you home with for Wednesday has you practice 2 other kinds of drawings. So a 6 and an 8, but I only make you fully draw out the 6. I only make you partially draw out the 8. I need to give you 2 other terms to completely understand an orbital drawing. So pi 2 can be referred to as a HOMO orbital. What that means is it is the highest occupied molecular orbital of this system. So pi 2 is the HOMO orbital of a 4-carbon conjugated system. Pi 3 also has its own label. Pi3 is known as LUMO. It is the lowest unoccupied molecular orbital of a 4-carbon conjugated system. So as we move forward into other chemistries, I'll have you be thinking about a HOMO orbital or a LUMO.
Does that have to be filled with 2 electrons?
Oh, so then orbitals, this would be, I can never remember all of the rules. Orbitals can only ever be filled with 2 electrons.
But if there's just one in Pi2, that's okay.
It would, yeah.
Doesn't have to be.
Right, yeah. So then, well, no. Okay, so I'm going to go ahead and get to Daniel's question because if I don't thoroughly answer it now, it's going to be confusing. So what Daniel was asking is if there is only 1 electron in Pi2, would it still be called a HOMO orbital? And the answer is actually no. But for reasons that are important for you all to know, so I'll just talk about it now. Where would the 4th electron have gone? So what you're saying is there's only 3, so I have only 1 electron in Pi2, the 4th electron had to go somewhere. And so then that would mean the 4th electron, if it weren't in Pi2, the 4th electron would have to be in Pi3. If that happens, Pi3 becomes the HOMO orbital, and then what would Pi4 be? The LUMO orbital. Yeah, and we're going to be moving electrons around. That's why it's okay for me to talk about this. Mine will come up today. Okay? We're going to move electrons around, and when we move electrons around, we have to readjust which orbitals we call HOMO and LUMO. Yep. Okay, any other follow-up questions? Okay, so first what I wanted to get to today was why are conjugated systems different? I've tried to go through and prove that. And so then this is, if you want to go back and look at PowerPoint, this is how I built our energy diagram. You can read through that if you want help building your 6 and 8 over the next day. So now what we need to talk about is unique chemistry. And we're going to just introduce one unique reaction today. So they have unique sharing of electrons, they have unique bond lengths, and the one unique chemistry we use with conjugated systems is known as Diels-Alder reaction. So the Diels-Alder reaction is so unique, it won a Nobel Prize. So in 1950, Otto Diels and Kurt Alder won the Nobel Prize for the Diels-Alder reaction. What is unique about it is we take 2 straight chains and we make a cyclic compound from it. That's why it's unique. So how many years have we had to study Diels-Alder since it was discovered and awarded a Nobel Prize? 70. So we're going to start with the basic Diels-Alder, and then I'm going to show you what we've done with it over the last 70 years, which is a lot. Because chemists are constantly going, I wonder what would happen if, and just fill in the blank. We've done lots of things. Okay, so we have 2 straight chain pieces we put together for a cyclo compound. So the diene piece, so we have a diene piece, that would be our 4-carbon piece of a classic Diels-Alder. We have a 4-carbon piece, and it is referred to as the diene. The second piece always has bonded to it an electron withdrawing group. The second piece, for the sake of communication, is called a dienophile. So how we describe a Diels-Alder reaction is that we have a reaction between a diene and a dienophile to give us a cyclohexene compound. So that's how we talk about the classic Diels-Alder reaction. So we have a 4-carbon piece with 2 double bonds, the diene, a 2-carbon piece with a withdrawing group, that's called the dienophile, to make a 6-carbon cyclohexene. So that's classic Diels-Alder. But as I've said, we've had 70 years to study. Isaac?
Oh, I was going to ask what the W is.
Withdrawing group. It's a withdrawing group. Okay, so I'm going to go ahead and forward to the next slide with, I forgot, another Valentine's. I'm dying to be with you. So another Valentine's card. Okay, so examples of Diels-Alder. So the diene part can have groups bonded to it. It can. So the diene piece can have other groups bonded to it. And then we put it together with the 2-carbon dienophile. What is my withdrawing group in the 2-carbon with dienophile that I have in pink up here at the top? Yep, cyanide, nitrile, exactly. Then I create a cyclohexene with lots of stuff around it. Okay, so then let's look at my second example. Oh, what's unique about this diene in my second example? It's cyclic itself. So the diene can be in a cyclic structure. What's unique about this dienophile? So in the middle, instead of a double bond, I have a triple bond. Instead of 1 electron withdrawing group, I have 2 electron withdrawing groups. And the final product, is it just a cyclo compound? No, instead it is a bicyclo compound. Okay, and so then these are all of the unique reactions. We're going to be drawing more of these out later. So if you don't have all of these drawn in your notes, that's okay. This is just examples of how unique Diels-Alder can be. What we need to get to is we need to talk about the concerted reaction. So this reaction concerted, it happens all in one step, all at once. So what kind of intermediate do we not have? We don't have a carbocation. It happens all at once. Okay, this picture, impossible for you to really draw in your notes. So for now, I want you to more look at me, and then you can refer to this picture in your textbook as you're reading for Wednesday. So I filled up here with my model a diene, and I have a dienophile. What I want you to notice about the diene is at these end carbons. So at these end carbons, these carbons are bonded to 2 different groups. The ones that are inside, so these are referred to as the inside groups. They also go by the name endo. These are the endo groups. These 2 that are kind of pointing out in a way are called the exo groups. So I have my diene wrapped around on itself in s-cis, and that puts the 2 inside groups in endo, these 2 outside groups in exo. So how we now know Diels-Alder happens, so I'm going to make this flat within one plane, is that the dienophile comes in from underneath. So we call that the endo rule. It comes in underneath where these 2 endo groups are. So it comes in from underneath. So in your mind, we need to imagine p orbitals at each of these carbons. So the tops of the p orbitals of the dienophile form interaction with the bottom of the p orbital from the diene. So can you see that a little bit in your mind? So we're imagining these big orbitals, these big balloons above and below my model. So the top lobe of the dienophile interacts with the bottom lobe of the diene. Okay, so then just like that. So in the last 2 minutes, I need to skip ahead to another drawing that sets you up for your worksheet to do for Wednesday. So then how our drawings work, so I'm forwarding ahead, we'll come back to all of this on Wednesday, and I skipped over. But for the mechanism of the reaction, if we lay out the 4-carbon HOMO orbital of the diene, so the HOMO orbital of the diene, if we lay out those 4 carbons, we see that we get constructive orbital overlap with the LUMO orbital of the dienophile. So the LUMO orbital was our 2-carbon system. So 1, 2, you should have this in your notes. So pi 1 was plus plus, pi 2, the LUMO orbital is plus minus. And we can see that we can take this plus minus, reorient it the other way, and then it fits right under that HOMO orbital of the diene. So that is the symmetry of the Diels-Alder reaction. So that the 4-carbon piece and the 2-carbon They overlap, they have constructive overlap of the p orbitals, and that is how we get our 6-member ring. So for the worksheet that I have you doing for Wednesday is I'm having you draw out what do you think about the possibility of a 6 plus 2 Diels-Alder and an 8 plus 2 Diels-Alder. Will they also be symmetric and have the 2 pieces align up? So you might find that you need to go through and look at this again in your book. So certainly my 10-minute introduction isn't enough for you to gain mastery over this topic. And so I have the worksheet for you to do drawing. You have ways writing of how to think about HOMO overlapping with HOMO. And so then as you do this worksheet, that's exactly the section that you need to go to in your textbook is the HOMO overlapping with the LUMO for Diels-Alder. That's the one section you really need to focus on to get this done for Wednesday. Okay, so then that gets us started on the unique reaction of Diels-Alder, getting into a little bit of the mechanism, and then we will get into all of the variations of Diels-Alder on Wednesday. Okay, so I'm just going to open this up here for you to see that. It's just one page. Yeah, and it needs to be done as much as you can, which may require you're also in your book great explanations as well, depending on the content.
No.